So good morning. I am Cheve Iver Refrea of OL116, and here I will be discussing experiment 3, Kirchhoff's law. So before we tackle the lab report for experiment 3, so we will first have a brief run through on the background and concepts regarding Kirchhoff's law. So first off, Kirchhoff's current law, or KCL, is Kirchhoff's first law that deals with the conservation of charge entering and leaving a junction. So to determine the amount of magnitude of the electrical current flowing around an electrical or electronic circuit, we need to use certain laws or rules that allows us to write down these currents in the form of an equation. The network equations used are those according to Kirchhoff's laws, and as we are dealing with circuit currents, we will be looking at Kirchhoff's current law, or KCL. So Gustav Kirchhoff's current law is one of the fundamental laws used for circuit analysis. His current law states that for a parallel path, the total current entering a circuit's junction is exactly equal to the current leaving the same junction. This is because it has no other place to go as no charge is lost. In other words, the algebraic sum of all the currents entering and leaving a junction must be equal to zero. The summation of in equals the summation of out. This idea by Kirchhoff is commonly known as the conservation of charge, as the current is conserved around the junction with no loss of current. So there. So that talks about the KCL. Now we will be talking about the KVL, or Kirchhoff's voltage law. So it is the second law that deals with the conservation of energy around a closed circuit path. So Kirchhoff's voltage law is the second of his fundamental laws, which we can use for circuit analysis. His voltage law states that for a closed loop series path, the algebraic sum of all the voltage around any closed loop in a circuit is equal to zero. This is because a circuit loop is closed conducting path, so no energy is lost. In other words, the algebraic sum of all the potential differences around the loop must be equal to zero. So note here that the term algebraic sum means to take into account the polarities and signs of the sources and the voltage drops around the loop. This idea by Kirchhoff is commonly known as the conservation of energy. As moving around a closed loop or circuit, you will end up back to where you started in a circuit, and therefore back to the same initial potential with no loss of voltage around the loop. Hence, any voltage drops around the loop must be equal to any voltage sources met along the way. So when applying Kirchhoff's voltage law to a specific circuit element, it is important that we pay special attention to the algebraic signs, plus or minus or positive or negative, of the voltage drops across the elements and the EMFs of sources, otherwise our calculations may be wrong. So that is the brief background of KCL and KVL. So now knowing that, we will now dive into the experiment 3 lab report. So as you can see, in the experiment 3 lab report, this is the provided circuit by our professor, as you can see, and this is the complete setup of the experiment. So we will now go to Tina Pro to show this. So as you can see, this is the one that I have made for the complete setup of experiment 3. So as you can see, there are total of 5 different segments. For every resistor, there is an ammeter and a voltmeter. So as you see, this is the first one. This is the second one. This is the third one, the fourth one, and the fifth one. And the voltage is 15 as stated in the lab report. So let's going back to the lab report. So this is the complete setup that I have made previously. Going back to the lab report. So as you can see from the values run, so the first voltage is 2.78 volts. The second is 7.66 volts. The third one is 4.66 volts. The fourth one is 1.68 volts. The fifth one is 2.88 volts. And for the current, it's the first one is 13.92 milliamperes. The second one is also 13.92 milliamperes. The third one is 9.12 milliamperes, and the fourth and fifth one are 4.8 milliamperes respectively. So here again is the setup that I have made, which is complete. And when we decided to run, so let's try again running to make sure that the values are correct. And there, so it has appeared, as you can see, as I have stated before, the values are precisely here. It is also worth noting that the parameters include the first resistor is 200 ohms, the second one is 550 ohms, the third one is 500 ohms, the fourth one is 350 ohms, and while the fifth resistor is 600 ohms. So inputting all of that, while the value for the switch is 15. So as you can see, these are all the values as stated in the table. So moving on, so we are now going to solve for table 2. So this is the this is the first formula for the first item. So negative VS1, which is the switch, plus the voltage of the first resistor, the voltage of the fourth resistor, and the voltage of the second resistor must equal to 0, as stated in the Kirchhoff's voltage law. So the first value is negative 15 volts, since the value for the switch is 15. I'm sorry, the value for the switch is 15. Okay. Next one is for the voltage for resistor 1, which is 2.78, as stated here. The second one is for the fourth is the resistor 4, which is here 1.68, as stated here. And for the voltage for resistor 2 is 7.66, as stated here. So adding all that up, so it will result into 0 volts, as stated by the as stated in Kirchhoff's voltage law. So we are correct in this predicament. Next one is this one, the second item. So once again, it's the negative volt is negative 15, as stated from before. Next is from the voltage of resistor 1, as stated here as well. The voltage for resistor 3, which is 4.56, as stated here. And for the voltage for resistor 2, which is stated here. So performing this equation, it will result again into a 0 voltage, as stated in Kirchhoff's voltage law. And the third item, it's the formula for this is the negative voltage for R3 plus voltage for resistor 4 and voltage for resistor 5. So the voltage for resistor 3 is 4.56 here, but since it's a negative, so it will have a negative sign, plus the voltage for R4, which is 1.68, as stated here, and the voltage for resistor 5, which is stated here, 2.88 volts. So again, performing the equation, it will result into a 0 volts. And lastly, for the fourth item, so the formula is current 1 minus current 3 minus current 4, which should equal to 0. So the first one is 13.92 milliamperes, as stated here. Second one is I3, which is here, as correctly stated, 9.12 milliamperes. And lastly, is I4, which is 4.8 milliamperes, which is stated here. So that is the breakdown of the experiment 3. And that is all. Thank you for watching.